Tonight I want to show you that this quotient with a huge numerator divided by 43 is just a natural number, or it's not even a fraction. So what I'm going to do is write this as in modular arithmetic form. And so 40 factorial minus 21 over 43, a member of the positive integers, is absolutely equivalent to this modular arithmetic statement. Now, a lot of you may recall that you can rewrite this. You can replace the triple bars with just plain old equals and write down 40 factorial is equal to, let me write that. That's 40 factorial is equal to 21. Sorry, that's a mistake. This would be plus is equal to 21. 21 plus some multiple of 43. Now we'll just call that 43m. Okay, and m again, it would be another natural number. And folks, again, here's our original statement. We want to prove it is a natural number, and there's an equivalence between this statement and this statement right here, and it's easy to see that equivalence if you rewrite this modular arithmetic statement as 40 factorial is equal to 21, this number right here, plus some multiple of 43. Okay, now that's pretty easy to see because if you were to subtract this off, you just 40 factorial minus 21 is just 43m, and 43m divided by 43 would be a natural number called m. Okay, so if we can establish this guy right here, we'll be done. Okay, if we can prove this, we'll be done. Now, a lot of you already probably suspect Wilson's theorem is the useful tool here, and it certainly is in this case. The more general form of Wilson's theorem is proved in every number theory course or every number theory book I've ever seen. But p minus 1 factorial is always congruent to p minus 1, and that's the same as just negative 1 since p is congruent to 0. All right, mod p. But anyway, this is congruent to negative 1. And this is a general statement. This is a special case of Wilson's theorem that I've written down. Okay, so mod 43. So this is the general result, very famous result. And so anyway, here we go. So we have this, okay? So we know this is our starting point. We want to get to this, but this will be our starting point, and we'll proceed in a way that's not unlike just basic algebra or arithmetic. What I'm going to do first is multiply through by 42, and the reason for that is that 42 is the same as 43 minus 1, right? Okay, that's certainly equal to 42, right? And when you square this, since 43 is just congruent to 0 mod 43, this is just going to be congruent to 1. Okay? See how that happened? That's this 1 that you see right here. All right? So that's all that happened right there. We did this, and the nice thing about this is that 42 times 41 factorial is 42 factorial. We made use of that. That's where the squared comes from. You see, there's already a 42 here, but if we multiply by another 42, we get 42 squared. But that has the merit of just being congruent to 1. It's its own arithmetic inverse. Okay? And in a similar fashion right here, we're going to get that 41 squared is congruent to 4. Okay? And again, you can just see that 43 minus, I'll just write it out. 43 minus 2, quantity squared, right? Okay, well again, 43 is congruent to 0. When you square this, you get 4. All right, so that's this 4 that you see right here. Okay, so we're sitting pretty at this point. 4 factorial is congruent to 41. Now, but this next step might look a little mysterious, but here's the trick. 4 times 11 is congruent to 1. Right? That's because, and let me go ahead and write it out for just specificity here. Mod 43. Okay? So you see what happened right here? When we multiplied this by 11, it just became 1. So you can think of a 1 sitting right here if you want to. You see, folks? That's a big fat 1 in front of the 40. You see there? Isn't that cool? 4 times 11 congruent to 1 means 4 and 11 are what they call multiplicative inverses, arithmetic inverses, something like that in number theory, okay? But the one you see right here is exactly this one here. You see, because we hit this with an 11, 44 is congruent to 1. Let me write this just to, 44 is congruent to 1, mod 43, okay? So we're left with this. Now, folks, the arithmetic on this, 11 times 41 is definitely doable. This is equal to 451. Notice I'm not using congruent anymore, okay? See, this is equal to 451, but 451 is congruent to 21. Now, I'll tell you why right underneath. It's fairly basic arithmetic, just long division. What you get here is 451. 451 is equal to 10 times 43. And you see, modular arithmetic is sometimes called remainder arithmetic because of what I'm doing right now. Okay? So, y'all, there we go. And y'all, what do? We just prove what we wanted to prove. We have 40 factorial. Remember what we needed to show? We needed to show that 40 factorial is congruent to 21 mod 43. And all of these were, I didn't write the mod 43, but everything was mod 43. And so right here, let me just write, we did prove that 40 factorial is congruent to 21. And again, we're definitely dealing in modulo 43. Okay. So yeah, that's QED time. We've completed this, if you want to call it a proof or demonstration, QED. And I may do another video that the general structure of this thing, if you really take a look at this, folks, this is kind of cool right here all by itself. This is the same as saying P minus 3. And this would be, sometimes the general proof is easier than a special case proof in arithmetic sense. But so you have P minus 3 factorial, right? Where P is 43, minus P minus 1 over 2. Okay? All over, and did I leave room here? Yeah, all over P. So y'all, in this particular case, P was 43, P a prime number. Here's your P, and then 43 minus 1 is 42. 42 divided by 2 is the 21 that you see right here. So this is a general truth that sometimes appears as an exercise in a number theory textbook when people are learning modular arithmetic. Now, notice that P is an odd integer most of the time. This would evaluate to an integer all by itself. But you can think of division by 2 as multiplication by the arithmetic inverse of 2. Okay, that's sort of what happened down here when we did the 4 and the 11 business. But anyway, that's all. Hope you enjoyed that. And again, by the way, this is a huge number. It's in the decadillion something. 40 factorial all by itself is an unpronounceable number. So anyway, we've proved what we set out to prove, and I hope you enjoyed.